February 8, 1942, Jakarta Airfield, Java. The Boeing B-17E Flying Fortress, serial number 41-2471, sat abandoned on the tropical airstrip, its American crew having evacuated the advancing Japanese forces just hours earlier. The aircraft belonged to the 7th Bomb Group of the United States Army Air Forces. Although damaged during a crash landing, it remained largely intact. Within days, Japanese troops would discover this bomber along with others scattered across Java's captured airfields. What they would learn from inspecting these planes would profoundly challenge their understanding of American industrial capacity. The aircraft represented more than mere military equipment. It embodied an entire philosophy of manufacturing that contrasted sharply with Japanese production methods. Over the next 3 years, Japanese engineers systematically examined captured B-17s, recording every aspect of their construction. Their findings would seriously undermine confidence in Japan's ability to match American industrial output. The discovery began in March 1942, as Japanese forces completed their conquest of the Dutch East Indies. At Mayoan Field in Java, engineers found B-17E serial number 41-2471 in remarkably good condition despite missing its nose section and engines. Nearby airfields held additional B-17s in varying states of damage. Toro Saito, an aviation correspondent from Asahi Press who toured Java's captured bases immediately after the occupation, documented the findings. He counted 4 B-17Es being prepared for evaluation, 1 at Milan, another at Cirebon, and 2 more at Bandung. The maintenance facilities for the B-17 in Java were exceptional for the period and conditions. Saito later wrote, "It seemed Bandung Field was the principal maintenance hub for the Americans, and it was here that Japanese technicians from the JICAN carried out their initial evaluation." The JICAN, formerly known as the Koku Jujutsu Kenkyujo, or Air Technical Research Institute, represented the pinnacle of Japanese aeronautical engineering. Based at Tachikawa Airfield near Tokyo, this organization employed Japan's leading aircraft designers and engineers. When news reached Tokyo that intact B-17 bombers had been captured, the JICAN promptly dispatched technical teams to Java. The Japanese faced a significant challenge preparing the captured planes for study. The B-17E was the most advanced version American forces had deployed to the Pacific at that stage of the war. Its systems were more complex than anything the Japanese military had encountered. Using parts salvaged from multiple damaged B-17s and employing captured Allied mechanics pressed into service, Japanese engineers began the painstaking work of restoring at least 2 B-17Es to flying condition. The effort required months of meticulous labor. Engineers had to comprehend electrical systems, hydraulic systems, and engine installations that differed fundamentally from Japanese designs. They studied manuals captured along with the aircraft, translating technical documentation and learning American engineering methods. By late 1942, Japanese engineers had successfully restored 2 B-17Es to airworthy status. A third aircraft, a B-17D captured at Clark Field in the Philippines, had already been flown to Japan earlier that year. The decision was made to transport the restored Java B-17Es to Japan for comprehensive assessment. The journey required careful planning, covering thousands of miles over territories recently conquered by Japanese forces. Elaborate flight plans ensured Japanese air defenses would not mistakenly engage the bombers. Fighter escorts were assigned, and a Nakajima L-2D transport, a license-built version of the Douglas DC-3, accompanied the planes as a mothership. Every air defense unit along the route received advanced notification. By May or June 1943, the 2 B-17Es arrived safely at Tachikawa Airfield near Tokyo, joining the B-17D previously flown from the Philippines. Japanese engineers now had 3 examples of America's primary heavy bomber for detailed examination. Major Kazuyuki Saito of the Imperial Japanese Army Air Force led the evaluation team at Tachikawa. An experienced aeronautical engineer, Saito assembled a team of specialists, including Lieutenants Shiyama and Kurusu, Ohara, and Army Assistant Engineer Shimamura. Major Uno and Captain Yagi served as test pilots, while Army Engineer Kaneo studied the engines and propulsion systems in detail. The mission was clear: document every element of the B-17's design, construction, and capabilities. With complete instruction manuals captured alongside the aircraft, no detail would be overlooked. Every system was tested, every component analyzed, every manufacturing technique scrutinized. The examination began with the airframe. Engineers measured rivet spacing, panel thickness, and structural member dimensions. They immediately recognized the remarkable consistency in construction across all 3 aircraft. Rivet holes aligned precisely, structural parts appeared interchangeable, and panels showed identical characteristics on multiple examples. This was not the work of individual craftsmen tailoring parts to fit each airframe. it was systematic mass production using standardized components manufactured to exacting tolerances. In contrast, Japanese aircraft production relied heavily on skilled artisans who fitted components individually. No two Japanese planes were identical. Parts from one aircraft often needed adjustment before installation on another, and field repairs demanded highly trained technicians. The American approach seemed fundamentally different. Any properly manufactured part would fit any aircraft of the same model without modification. This level of standardization required precision that Japanese factories had not achieved. The engines offered even more dramatic evidence of American mass production. The Wright R-1820 Cyclone radial engines powering the B-17 contained hundreds of precisely machined components. Engineers disassembled the engines entirely, measuring clearances and tolerances. Every part, crankshafts, connecting rods, cylinders, pistons, showed identical dimensions across different engines. Field manuals confirmed that American mechanics could replace major components without adjustment. A cylinder from one engine would fit perfectly in another. A crankshaft was interchangeable with any identical model. In contrast, Japanese engines required skilled assembly by experienced technicians, with components often hand-fitted to achieve correct clearances. Field maintenance demanded mechanics who could adjust and modify parts. The American system eliminated this need, embedding precision directly into manufacturing. Hydraulic and electrical systems demonstrated similar standardization. Actuators, valves, and control lines used standardized fittings. Wiring employed machine-crimped terminals rather than hand-soldered joints, and gauges were uniform throughout the aircraft. Circuit breakers, switches, and instruments were modular, enabling quick replacement. The crew oxygen system featured precision regulators controlling flow to each station. Whereas Japanese regulators demanded highly trained specialists, these 17 regulators could be produced by automobile manufacturers applying their existing capabilities to aviation. The bomb release mechanisms reflected the same design philosophy. Japanese bomb racks required careful calibration, while B-17 shackles were self-adjusting and required no manual adjustment. Defensive armament further impressed Japanese pilots. 13.50 caliber Browning M2 machine guns provided overlapping fields of fire, covering nearly every approach. While the guns were simpler and built to looser tolerances than Japanese weapons, they functioned reliably through robust engineering rather than precision craftsmanship. Any competent armorer could maintain them with basic tools. By autumn 1943, all three captured B-17s flew regularly from Fusa Airfield near Tachikawa. Japanese pilots gained hands-on experience, documenting handling characteristics, performance, and operational procedures. Training films showed Ki-43 and Ki-44 fighters practicing attacks against the captured bombers, sometimes featuring a repainted B-17D and an escorted Curtiss P-40 for realism. Public theaters screened these films as propaganda, depicting Japanese fighters engaging American bombers successfully. However, extensive practice revealed a sobering truth. Even when fighters successfully attacked, the B-17's defensive firepower and structural strength made it a formidable opponent. More troubling, for every bomber destroyed, American factories could produce replacements faster than Japanese industry could replace lost aircraft. In February 1943, Asahi Press published Anatomy of the Enemy's Aircraft, a comprehensive analysis of captured Allied planes, particularly the B-17. Photographs, technical drawings, and specifications documented every major system. The book became required reading for Japanese aircraft engineers. Mitsubishi engineer Hisanojo Ozawa, designer of the K-21 and K-67 bombers, contributed an article analyzing the B-17. Ozawa noted that although the B-17E evolved from a 1935 design, improvements had made it a first-line combat aircraft. Shizu Kikahara, designer of the Kawanishi H-8K flying boat, praised the captured B-17s for their sophisticated subsystem integration and the simplicity of cockpit controls relative to the aircraft's size. What these analyses carefully avoided stating explicitly was the most troubling conclusion. Japanese engineers recognized the technological superiority of American mass production and engineering practices, a gap they could not close quickly. The B-7's construction methods represented a level of industrial organization that Japanese factories could not match. The aircraft was not superior because of better aerodynamic design or more powerful engines. It was superior because American industry could produce it in quantities that would overwhelm Japanese air defenses through sheer numbers. The examination revealed the B-7's construction in extensive detail. Wing panels were stamped from dies rather than hand-formed over wooden forms. This required massive hydraulic presses and precision dies costing fortunes to produce. But once those dies existed, workers could stamp panels by the hundreds per day. Control surfaces. showed identical forming. Every aileron, elevator, and rudder section appeared to have been produced from master tooling rather than individually crafted. The main wing spars, critical structural members carrying flight loads, were machined on automated equipment. Drilling patterns matched exactly across multiple aircraft. Any wing rib from one bomber would fit precisely into another aircraft of the same model. The landing gear demonstrated automated precision. Machining. Main struts were forged components, heat-treated and machined on automated lathes. Actuating mechanisms consisted of hardened components, machined to identical specifications. In early 1944, one of the captured B-17 Easy was damaged beyond repair in a ground accident. During takeoff from Fosse Airfield, the aircraft was caught in an unexpected crosswind. Its right wing collided with a parked Ki-49 bomber. Both aircraft were destroyed. The incident provided an opportunity for destructive examination. Engineers could cut into the damaged wing structure to examine construction details not visible in intact aircraft. By cutting through the wing skin and structure, engineers could measure rivet installation with precision. Hundreds of rivets were measured. Diameter variation proved minimal, less than 20,000 of an inch. Installation depth varied by less than 0.1/000th of an inch. Such consistency across thousands of rivets was impossible to achieve through hand riveting. The aircraft had clearly been assembled using automated or semi-automated riveting equipment. The implications extended beyond the immediate question of how one aircraft was built. If American factories could produce B-7 with this level of consistency, they could produce them rapidly. If parts were truly interchangeable, field maintenance became dramatically simpler. If workers needed less skill because precision was built into the tooling rather than the craftsman, production could scale up quickly by training new workers. Japanese aircraft production faced exactly the opposite situation. Skilled craftsmen remained in short supply. Training new workers to the required skill levels took years. Increasing production meant finding and training more skilled workers, not simply adding more assembly stations. In May 1945, American photographic reconnaissance over Tachikawa Airfield captured images that puzzled intelligence analysts. Clearly visible was what appeared to be a new type of Japanese 4INE bomber or transport. Analysts estimated the aircraft's wingspan at approximately 104 feet. The mysterious aircraft was designated Tachikawa 104 based on the estimated wingspan and its location. As weeks passed without additional information, speculation grew about Japan's apparent development of a new heavy aircraft. Despite intensive bombing of Japanese aircraft factories, none of the American analysts who examined the photographs suspected the truth. The mysterious aircraft was actually one of their own B-17E flying fortresses, still undergoing evaluation by Japanese engineers 4 years after its capture. The actual wingspan of the B-17 measured 103 feet 9 inches, making the American intelligence estimate remarkably accurate. The extensive evaluation of captured B-7s had surprisingly little impact on Japanese bomber design. Japan attempted to copy the Douglas DC-4E transport as the Nakajima G5N bomber, but its other 4INE land-based bomber, the Nakajima G8N, which entered production near the war's end, used more advanced structural designs that gained nothing from the B-7's airframe engineering. There is evidence, however, that components and systems from the B-17 influenced later Japanese aircraft. Most notable were attempts to perfect turbo superchargers for high-altitude performance. Several advanced Japanese designs including the Army's Tachikawa K-74, Mitsubishi Ki-83 and Nakajima K-87 as well as the Navy's G8N and Mitsubishi J2M failed to reach their full potential, mainly because Japan could not successfully implement turbo supercharger technology. The problem was not understanding the technology. Japanese engineers who examined the B-17 understood how turbo superchargers worked. The problem was manufacturing. Turbo superchargers required high-temperature alloys and precision manufacturing that Japanese industry could not consistently produce. Even when experimental units were built, they proved unreliable. The same manufacturing limitations that prevented mass production of standardized B-17 components prevented development of advanced engine technologies. By 1944, the cumulative evidence from examining captured American aircraft had led thoughtful Japanese engineers to sobering conclusions about relative industrial capabilities. American aircraft production reached 96,000 aircraft in 1944. Japan struggled to produce 28,000, but the disparity in numbers understated the real gap. American aircraft consisted of thousands of precisely manufactured interchangeable parts. They could be maintained by mechanics with basic training using standardized replacement components. They could be repaired in the field quickly and returned to service. Japanese aircraft remained craftsman-built machines requiring skilled technicians for maintenance, specialized parts for repairs, and constant adjustment to remain operational. Each American aircraft represented greater actual combat capability because it could be kept flying with less effort and fewer specialized resources. The production system that enabled this output was visible in the B-17's construction. Boeing's Plant 2 in Seattle had produced 6,981 B-17 by the time production ended in April 1945. At peak production, 16 complete B-17 rolled off the assembly line every day. Douglas Aircraft in Long Beach produced 3,000 B-17s between July 1942 and July 1945. Lockheed Vega in Burbank built 2,750 B-7s between August 1942 and August 1945. 1945, total B-7 production reached 12,731 aircraft from all three manufacturers. The Japanese engineers examining captured B-17s in 1943 and 1944 had no access to these production statistics, but they could calculate approximate production rates based on observed serial numbers and construction dates documented in the aircraft. The mathematics proved devastating. If American factories could build B-7s with such precision and consistency, they could build them rapidly. If they could build heavy bombers this quickly, their production of fighters and other aircraft must be proportionally greater. Japan had entered a war of industrial attrition against an opponent with 10 or 20 times its manufacturing capacity. The strategic bombing campaign against Japan's aircraft industry, which intensified in 1944, destroyed any remaining hope for matching American production. Boeing B-29 Super Fortresses, the B-7's larger and more advanced successor, appeared over Japan in formations that Japanese defenses could not stop. Each raid destroyed production capacity that could not be replaced. The Nakajima plant at Musashina, the Mitsubishi facilities at Nagoya, the Kawasaki factories, all suffered severe damage from precision bombing. An earthquake in January 1945 compounded the damage to Mitsubishi's supplier network. The combination of bombing and earthquake collapsed Japanese aircraft production. By early 1945, monthly output had fallen from over 2,500 airframes in May 1944 to barely 1,500. The decline continued through the final months of the war. After Japan's surrender in August 1945, the United States Strategic Bombing Survey conducted comprehensive examinations of Japanese war production. Teams of American engineers toured Japanese aircraft factories, documenting production methods and assessing industrial capabilities. What they found confirmed the conclusions that perceptive Japanese engineers had reached through examining captured B-17s. Japanese aircraft production relied heavily on skilled manual labor. Standardization remained limited. Interchangeable parts were more aspiration than reality across much of the industry. Subcontracting networks provided components, but quality control and dimensional consistency proved problematic. American engineers touring the Mitsubishi facilities at Nagoya observed skilled craftsmen hand-forming aluminum panels that would have been die-stamped in American factories. Manual riveting predominated where American factories used automated riveters. Individual fitting and adjustment were common where American factories used precision-manufactured interchangeable parts. The survey concluded that Japanese aircraft factories had been organized appropriately for producing hundreds of aircraft. American factories had been organized for producing hundreds of thousands. No amount of determination or skill could overcome that fundamental disparity in industrial organization. The captured B-17s examined at Takiowa from 1943 through 1945 were destroyed in the war's final months, either by American bombing or by Japanese authorities, eliminating evidence. But the lessons those aircraft taught survived in the minds of the engineers who had studied them so carefully. In the decades following the war, Japanese industry underwent a transformation more profound than anything attempted during wartime. Engineers who had examined American aircraft and documented American production methods brought those lessons to Japan's post-war reconstruction. They understood that matching American industrial capability required not just copying American products, but implementing American production systems. The transformation required 20 years. Japanese factories that had relied on skilled craftsmen reorganized around precision machinery and automated processes. Industries that had valued individual craftsmanship learned to value systematic efficiency. Manufacturing that had been organized as collections of skilled workers evolved into integrated production systems. By the mid-1960s, Japanese factories were producing automobiles and electronics, using automated production methods comparable to American factories. By the 1970s, Japanese manufacturers had refined those methods, developing production systems like Toyota's just-in-time manufacturing that improved on American mass production techniques. The skilled craftsmen remained valued in Japanese industry, but their role had changed. Instead of individually crafting products, they designed production systems and tooling that enabled less skilled workers to produce precisely manufactured products at scale. The precision that had once come from the craftsman's skill now came from the precision of the tooling and equipment. Companies like Toyota, Sony, and Honda became global leaders by combining Japanese attention to detail with American systematic production methods. The quality that Japanese products became known for resulted from production systems designed to build quality into the process rather than relying on skilled workers to individually craft quality products. In the 1980s, when American manufacturers faced intense competition from Japanese imports, American engineers toured Japanese factories to learn efficiency techniques. The irony was not lost on those who remembered the wartime examination of captured American aircraft. The story of Japanese engineers examining captured B-7 bombers became a case study in Japanese engineering schools. It illustrated how examining an opponent's products could reveal fundamental principles of industrial organization. It demonstrated that success required understanding not just what competitors produced, but how they produced it. The captured B-17s had taught Japanese engineers that modern industrial warfare was won not by superior craftsmanship, but by superior production systems, not by building better individual aircraft, but by building adequate aircraft in overwhelming numbers, not by skilled workers, but by systematic processes that enabled less skilled workers to produce precisely manufactured products rapidly. Those insights gained through careful analysis of enemy equipment during wartime became the foundation for Japan's post-war industrial resurgence. The transformation of Japanese manufacturing from artisan-based production to organized mass production represented the ultimate triumph of the principles embodied in those captured B-17s studied at Tachikawa. The engineers who had measured rivets and recorded production techniques in 1943 and 1944 became the architects of Japan's industrial revival. They had learned by inspecting aluminum and machinery that modern industry belonged not to those with the most skilled craftsmen but to those with the most efficient production systems. In contemporary manufacturing engineering courses, the story serves as a case study in how evaluating competitors' products can reveal hidden systems and methodologies. It demonstrates that comprehending an opponent's processes matters more than merely copying their designs. It shows that production principles ultimately determine the outcomes of industrial competition. The Boeing B-17 Flying Fortress dropped 640,000 tons of bombs during World War II. It earned its status as one of history's most effective heavy bombers through operational missions across every theater. Yet perhaps its most significant contribution to history was not the sorties it flew, but the lessons it imparted when Japanese engineers examined captured examples. Those engineers discovered that American industrial strength stemmed not from superior materials or advanced designs, but from superior organization of the manufacturing process. They observed that standardization, precision tooling, interchangeable components, and methodical production practices could accomplish what skillful craftsmanship alone could not: the ability to produce complex machines quickly and in quantities limited only by available resources. The captured B-17s analyzed at Tachikawa are gone, destroyed more than 70 years ago. But the insights they provided reshaped Japanese industry and influenced manufacturing worldwide. Engineers and producers globally learned that mass production and quality were not contradictory but complementary facets of properly structured industrial systems. The story that began in February 1942 on a muddy Java airfield with a damaged Boeing B-17E awaiting capture by advancing Japanese forces concluded decades later with Japan and America as collaborators in advancing manufacturing technology. The study of those captured bombers had taught Japanese engineers that their defeat had been inevitable. More importantly, it taught them why, and in understanding why, they learned how to prevent industrial shortcomings from ever again constraining Japan's capabilities. The Boeing B-17 Flying Fortress served as a teacher to its former adversaries, and they absorbed the lesson thoroughly.